This is the second lecture on cross products. In this lecture, we will discuss how to use coordinates to compute this cross product, and we will also discuss the triple scalar product. We're going to make use of the results that were derived from the coordinate-free definition of the vector. These include the results for the standard basis vectors. In particular, we will use these properties, and they will enable us to find a very easy way to use components to compute cross products. So if we recall, the vectors, the basis vectors have a certain pattern. We developed it using, or this was our shorthand for it, was the circle. And since these vectors are all related by the right-hand rule, they essentially turn into one another, but there can be sign changes depending on the order. We are also going to make use of these results, or these properties of the cross product, in particular that the cross product is distributive over addition, and also that it's associative with respect to scalar multiplication. To start using components to calculate the cross product, we first write out this cross product in terms of the components of u and v. And then we use the distributive property. Remember, cross product is distributive over addition, and here we have, of course, the addition with these plus signs all over. And we'll use that to essentially FOIL this expression. So we're going to do an aggravated FOIL of the cross product written in component form. So let's look at the first term. We will have ux, unit vector I, cross vx, unit vector I. So I did those two terms and took the cross product of them. Okay. Now, because of scalar multiplication, because of the associative property with respect to scalar multiplication, we can essentially factor out the scalars ux and vx. These are scalars, and we're left with this cross product of the two basis vectors, in this case I cross I. That's how this next expression is developed with all of its 9 terms. So here's the first one, and it becomes that term. Then if we take this with respect to the j component of v, we get the next term. Once this is done, we use the property of the basis vectors from that circle. If you want to see the circle again, here it is. Put it up here. And we have I, j, k. And we apply the results. The first thing, though, we can do is eliminate some terms. Cross product is 0 if vectors are parallel. Well, that of course applies to vectors that are the same. So I cross I is going to be 0. So all these terms out. J cross j is 0. K cross k is 0. So that eliminates 3 out of the 9 terms. We're going to look at the rest. I cross j, I'll be going around the circle in this direction with the arrows. This is k. Now let's look over here and find another case where we have I and j in a cross product, and it's down here. But this time it's j cross I. This becomes minus k. So I'm going to take these two terms, I'll highlight them here, and I'm going to write them down here. Good. So you can see at first we get ux vy, and then we must subtract uy vx, and that gives me a k term. Do the same thing for the others. I cross k is going the wrong way around the circle. That's minus j. And down here we have k cross I, which will give us j, and that makes up this next term. The reason there's a negative sign here is that I put the ux vz term first, and that's the reason for that. We'll see in a minute. And then of course the next one, j cross k is I, and here we have k cross j, which is minus I, and that gives us the leading term. Now nobody computes the vector cross product in this way. No, it's not done like this. What happens now is that this step, well, what has been done in the past, is that this, this result is recognized as the determinant of a matrix. This would be of a 3 by 3 matrix. And the 3 by 3 matrix is used to compute the cross product. So in other words, we don't go through all this IJK business, we use the result. And here's the matrix that we need to get that result. It has this particular form. You actually could put the IJK in a different row, but don't do that at all for now. We're going to leave it up here in the top row. IJK must be in the top row. Then we're taking the cross product of U cross V, and since U is the first vector, it goes here, and the V goes down in the third row. Not only does this give us the result that we need, but you can notice too that if you're taking the determinant of a matrix and you swap two of the rows, the sign changes. And swapping rows 2 and 3, I'm just do an arrow like this, meaning I'm going to put the V's up in the second row and U's down in the third row. We would have V cross U. It would be the negative of the cross product U cross V, and that's what we expect because cross product is anti-commutative, and you can see that's already built in to the determinant. So the important point for doing this work is that this needs to be a square matrix. You can't take the determinant of a matrix that's not square. In this case, it's going to be a 3 by 3 matrix. The top row, I'll highlight it again, has to be the IJK terms. The next row is the first vector, and the second vector goes in the third row. Second vector's components go in the third row. Occasionally, sometimes, students write only these two rows and then try to take a determinant, and after that they throw in the I, J, and K that they get from who knows where. That's not correct at all. The I, J, K need to go in the top row so you have a square matrix so you can take a determinant, and by putting the I, J, K in the top row you end up with I, J, and K in the answer, and since you have a vector product you expect that they will be there. The second thing, or maybe third or fourth thing that's demonstrated here is that the determinant needs to be taken for this class using the cofactor method. There's another method that people use sometimes called a diagonal method of taking a determinant, and that's not acceptable for this class. If you want to take the determinant using the diagonal method, okay, but then go ahead and take it also using the cofactor method. Okay, so you ask, why are we using the cofactor method? Well, first of all, the cofactor method generalizes to higher dimensions. If you remember, perhaps you looked at the written lecture for the introduction to this class, I included in there a list from Wikipedia of all the different fields of study for which Calculus 3 provides the tools. Many of the topics in that list had spaces that were not the same as this three-dimensional physical space that we are very used to. If you look at the problems in economics, for example, they have 6, 8 dimensional spaces that they're working with. So the cofactor matrix is used there, and that's one reason for learning it. Another reason is that the cofactor matrix is very useful when you're trying to take the determinant of a sparse matrix. A sparse matrix is one that has quite a few zeros in it, and by using the cofactor matrix you can take advantage of that to simplify the calculation. We will be taking determinants of sparse matrices later in the semester when we're looking for Jacobians. So let us discuss a little bit about this cofactor matrix method if you don't know it already. So for the cofactor method, and we're expanding around, okay, we want to expand along row 1. And there's a sign convention that you have to make use of. So we're expanding along row 1. The first term we put the I, no sign change. And then you find the cofactor matrix associated with that term by mentally crossing off the row and column where the I lives, and you're left with UI, UZ, VY, VZ, and that makes up the 2 by 2 matrix that follows I. Now repeat this for J. J, though, the second term in this 3 by 3 matrix has a negative sign in front. The negative sign doesn't really belong with J. It has to do with the determinant of the cofactor matrix, but it's written like this. Okay, so negative J, and then mentally crossing off the row and column containing J, we end up with UX, UZ, VX, VZ, and that makes up this 2 by 2 matrix for J. For K, it's the same thing. K has no sign change, and the cofactor matrix is UX, UI, VX, VY. And now we take the determinants. These are just 2 by 2, so it's not hard at all. And you can see we get exactly what we had before when we had all of those basis vectors and all those cross products. We don't even have to be concerned with that. It's just going to fall out from this determinant. Here's the I term. Here's the J term. Now sometimes people, which includes me at times, I have, decide to get rid of this negative sign, put it through here, and change the signs of what's inside of these parentheses. I don't advise doing it. When you leave that negative sign out there, you have, well, it's part of a paper trail through your solution. So if you end up with a sign problem, it's easier to find if you leave that negative sign right there. And that was, of course, the voice of experience talking. So here we have another determinant of the 2 by 2 matrix, 2 by 2 cofactor matrix multiplying K. We can go ahead and try an example. So we need components for U. Let's say U is 1, 2, 3, and V is 4, 5, 6. Not very imaginative, but okay, that'll work. So for U cross V, I construct first the matrix I, J, K, 1, 2, 3, 4, 5, 6. And I take the determinant using these cofactors. So the first, I will have the I, and then I have another matrix, which will be 2, 3, 5, and 6. minus J, another cofactor matrix, 1, 3, 4, and 6. And then, of course, the K term, 1, 2, 4, 5. I'm going to just take the determinants here. I would have 12 minus 15, negative 3i. Okay, 6 minus 12 gives me negative 6 here for the j. I'm going to leave it like that for a minute, although I will resolve those two negative signs. And then we have, what's this, a 4, right? I'm trouble writing with this pen. Okay, 6, no, I'm sorry, 5 minus 8, so it's another negative 3, and here's the k. Okay, and this is as expected. The cross product gives a vector, so when we're done, we expect to see either the ijk, or you can write it with brackets, but we expect a vector when we're done. Now, sometimes students do the work correctly and then are not sure of their result and think to be on the safe side, for example, with dot product, that maybe I should throw some ijk in there. But for the dot product, you don't expect it. They shouldn't be there. It's a scalar result. Here, for the u cross v, yes, it is a vector. And you will have, and using the components, you will have basis vectors in the answer. Now we'll apply what we know to find a good way to solve or to be able to calculate the scalar triple product. So this is the scalar triple product. One vector dotted with the cross product of two other vectors. There is a vector triple product, in case if you're wondering, and in that case, this dot is replaced by another cross product. The scalar triple product has a physical intuition or physical significance of being the volume of a parallelepiped. It's actually a box here. It's even called the box product sometimes. But this box, or parallelepiped, is formed by the vectors u, v, and w. U and v, the way this is written, make up the base. So here's u and here's v. If you remember, the cross product is the area. The magnitude of the cross product is the area. So u cross v is the area of the parallelogram formed by u and v. So that becomes the area of the base. And the w, of course, is slanted at an angle of theta. But to find the volume of this box, we need the height, and the height is the magnitude of w times the cosine of theta. All right, there we go, right. That's the other term. So here's the height, and the result is the volume. We signaled out u and v as the base because they are in the cross product. But if you looked at this box, you could have said that v and w were the base, turned it on its side, and that v and w are the base, and that u gives us the other dimension along the height of it. And that's perfectly valid. And so you can take the cross product using different order for these vectors, but you have to be careful when you look at the whole cross product, because if you just change, for example, if we went v cross u, the result would be negative. If you're looking only at the magnitude, of course, it will always be positive, but you can get another sign in there, and for that reason, just like the cross product, this is called the signed volume, because it's possible to get a negative result. Now, calculating this, you just write out the components, it would be a lot of work. I have Vx in the I direction. Let's write them out here for the for W. And that's going to have to be the dot product of all the terms associated with U cross V. I'm just going to write the first one. I'll have and of course we have J and K terms. Okay, so we take this dot product. The only thing that's going to count for Wx are the I terms. So this will end up being Wx times Uy Vz minus Uz Vy. And that is a scalar result as we expect. It's called the scalar triple product, and we see the dot product in here, and that's what makes it into a scalar. I'm not going to write out the rest of these terms, but the conclusion from this is that, just like in the previous case, the answer here is the determinant of a 3 by 3 matrix. But in this case, instead of having ijk in the top row, we have wx, wy, and wz. So here's your matrix for your triple scalar product. And to work it out, Wx times that cofactor and from this the scalar triple product can be evaluated. Let's go back to our original look at the scalar triple product and note some special cases. These cases are not surprising, but they just make a nice connection between the dot and cross products and, of course, physical intuition, or rather physical reality. If U is parallel to V, so instead of having V out there, we'll have V here right on top of U, then the box would have a zero volume. When we look at this expression, if U and V are parallel, the cross product of parallel vectors is 0. For a second special case, these are more pitiful than special cases, if this angle between W and the cross product of U cross V, which is normal to the plane of the base, if that is pi over 2, that means the box has collapsed, and again it has 0 volume. And we can see where this comes from the dot and the cross products. The dot product of two perpendicular vectors is 0, and that would be the case. If U cross V and W are at an angle of pi over 2 at right angles, then they are perpendicular, and that dot product would be 0.